Switchgear refers to the combined electrical equipment used to make, carry, and break electrical circuits in a power system. This includes devices such as circuit breakers, fuses, contactors, relays, voltage transformers, and current transformers. Types of switchgear: low voltage, less than 1000 VAC, medium voltage, 1236 kVAC, high voltage above 36 kVAC. Switchgear is also categorized based on the type of insulation used, which can be air, oil, or gas. Our focus here is on gas-insulated switchgear. Gas-insulated switchgear is a type of electrical switchgear where most components are enclosed in gas-filled chambers. The primary gas used in GIS is sulfur hexafluoride SF6, which provides superior electrical insulation and arc quenching properties compared to air. This allows GIS to have a significantly smaller size and weight, making it ideal for confined, indoor spaces where high voltages are needed. The design of gas-insulated switchgear involves using a dielectric gas, typically sulfur hexafluoride SF6, to insulate various switchgear components within grounded, metal enclosures. The gas is maintained at a moderate pressure of 400 to 600 kilopascals to prevent leakage or condensation at low temperatures. SF6 is a colorless, inert gas that is approximately 5 times denser than air and provides 2 to 3 times better insulation. Its superior arc flash handling capability makes it about 100 times more effective than air. GIS components are pre-assembled and gas-filled at the factory, simplifying the installation process. The working principle of gas-insulated switchgear is based on using a dielectric gas, such as SF6, to insulate electrical equipment. SF6 offers several advantages, including excellent thermal and dielectric properties. GIS systems operate using a combination of vacuum and gas to isolate live parts. This design makes the switchgear highly compact and efficient, providing excellent reliability and low maintenance requirements. During arc flash quenching, SF6 decomposes, but the decomposition products typically reconstitute back to SF6, allowing the gas to remain effective over a long period. Gas-insulated switchgear has been evolving since the late 1960s and has become increasingly popular due to several key advantages. GIS switchgear is highly resistant to environmental conditions like moisture, dust, and salt air, which enhances its reliability and uptime. This makes it suitable for harsh environments such as coastal or desert areas. The components of GIS are sealed in a gas-filled enclosure, preventing exposure to the surrounding environment. This significantly reduces maintenance requirements since regular testing and inspection are not needed. GIS eliminates the need for air insulation, allowing it to be much smaller than air-insulated switchgear. This compactness is ideal for areas with limited space, such as indoor or urban settings. By enclosing components within modules, GIS prevents arc-causing incidents like vermin entry or conductive dust accumulation. This reduces arc flashes and increases overall safety. Additionally, SF6 is an excellent arc-quenching medium. GIS comes pre-assembled, making the installation process straightforward and quick. This leads to easier installations and shorter installation times. While gas-insulated switchgear has numerous advantages, it is essential to be aware of its limitations to make an informed decision between GIS and other types of switchgear, such as air or oil-insulated variants. The main drawbacks include high cost. One of the major disadvantages of GIS is its high initial cost compared to other types of switchgear. However, the long-term benefits, such as minimal maintenance, can offset the initial investment. Longer outages. If GIS experiences an internal fault, the sealed nature of the equipment can lead to longer repair times. Gas-insulated switchgear is commonly used in high-voltage applications like transmission and distribution and in medium-voltage settings such as substations. A gas-insulated substation offers benefits like a reduced footprint and high reliability. GIS is also gaining popularity in industrial and commercial properties. Its compact size makes it ideal for indoor or confined spaces, requiring significantly less space than conventional air-insulated switchgear. Additionally, GIS is suitable for underground installations, making it useful in areas with limited land space or specific environmental concerns, such as adverse weather or soil conditions. Common failures. GIS can fail due to SF6 gas leaks, excessive microwater in the gas, or component failures. Regular testing and maintenance are crucial to ensure safe and reliable operation. Users need a maintenance checklist to prevent failures, optimize performance, identify issues early, minimize outages, and extend lifespan. Annual checks and condition inspections every 5 to 10 years. Includes voltage withstand tests, contact resistance, relay operation, and other parameter checks. Components are usually lubricated for life, but occasional oiling may be needed after many years. May involve breaker replacement, SF6 gas removal or recharge, and other updates. Manufacturers provide specific maintenance guidelines, including frequency and procedures, ensuring the switchgear remains in good condition. Gas-insulated switchgear versus air-insulated switchgear. While both GIS and AIS serve similar functions, they differ mainly in their insulation mediums. Insulation medium, GIS uses gas, typically SF6, for insulation. AIS uses air for insulation. Advantages of GIS: compact and efficient. GIS is more compact and efficient, ideal for confined spaces. Construction: GIS components are housed in gas-filled, earthed modules, sealed for life. AIS components are generally accessible and withdrawable. Installation: GIS often comes pre-assembled, making it easier and faster to install, especially in remote or space-constrained locations. Maintenance: GIS requires minimal maintenance, unlike AIS, which needs regular upkeep due to exposure to environmental elements. Reliability: less susceptible to environmental conditions, making GIS more reliable in harsh environments. Higher initial cost: GIS tends to be more expensive upfront, 10 to 40% more due to its construction and use of SF6 gas. However, the long-term savings on maintenance can offset the initial investment. Applications: GIS is suitable for high voltage and medium voltage applications, urban settings, and areas with limited space. AIS remains valuable where initial cost is a major consideration and space is not an issue. Let us discuss main topic. Hybrid gas-insulated switchgear. HGIS offers significant environmental benefits by reducing SF6 gas consumption compared to traditional SF6 gas-insulated switchgear. GIS at the same voltage level. Here's a more detailed look at these benefits. Reduced SF6 gas consumption. HGIS can save up to 2/3 of SF6 gas consumption compared to conventional GIS. This reduction is achieved by combining gas-insulated components with solid insulated busbars, which eliminates the need for SF6 in certain parts of the switchgear. Environmental impact. SF6 is a potent greenhouse gas with a global warming potential GWP 24,300 times higher than CO2. By significantly reducing SF6 usage, HGIS helps lower the environmental footprint and mitigates the impact on climate change. Operational efficiency. HGIS systems are designed to be modular, making them easier to install, maintain, and upgrade. This modularity also allows for more flexible and efficient operation, reducing downtime and operational costs. Enhanced safety and reliability. The combination of gas-insulated and solid insulated components in HGIS enhances the overall safety and reliability of the switchgear. The solid insulated busbars reduce the risk of gas leaks and improve the system's resilience to environmental factors. Case studies and practical applications. Several case studies have demonstrated the effectiveness of HGIS in reducing SF6 gas consumption and improving environmental performance. For example, TAMCO's GV3 and 36 kV hybrid GIS switchgear uses around 30 to 50% less SF6 gas compared to conventional GIS switchgear. Future-ready solutions. HGIS is considered a future-ready solution for high-voltage electrical infrastructure, aligning with global sustainability goals and regulations aimed at reducing greenhouse gas emissions. Hybrid gas-insulated switchgear offers a more environmentally friendly alternative to traditional SF6 GIS by significantly reducing SF6 gas consumption, enhancing operational efficiency, and improving safety and reliability. Its adoption supports the transition to a greener and more sustainable power grid. Conventional gas-insulated switchgear. Traditional GIS systems are typically bulky and contain high amounts of SF6 gas, which has a substantial environmental footprint. Handling SF6 gas on site is a major concern. While plug-in busbars were introduced to mitigate on-site gas handling, they did not significantly reduce the overall SF6 content compared to conventional GIS. Hybrid switchgear advantages. Hybrid switchgear combines gas-insulated switchgear with solid insulated screened busbars, addressing many of the issues faced by utilities with traditional GIS. This hybrid approach eliminates the need for SF6 in the busbar compartment. Given the high global warming potential of SF6, reducing its use is crucial. The introduction of plug-in type voltage transformers and outer cone cable bushings, which can also accommodate current transformers, offers better accessibility and reduces the size of SF6 filled tanks restricted to switching units only. This leads to a 30 to 50% reduction in SF6 consumption. Modular design and its benefits. A wave of modularity is transforming switchgear design and installation. Subsystem modularity E.G, circuit breaker, and disconnecting switch modular design makes switchgear more maintenance-friendly and extends its life. Modular designs allow independent operation and servicing of each module without affecting others, which is significant for operations and maintenance. This approach also facilitates upgrades or rating enhancements retrofitting, providing greater flexibility for future growth and extending the lifespan of switchgear installations. Sustainability is described through three dimensions: environmental, economic, and social. It focuses on addressing major environmental issues such as climate change, biodiversity loss, ecosystem degradation, and pollution. Sustainability is increasingly vital across all industries as companies strive to balance economic success with long-term values that support efforts against climate change and ensure social progress for all stakeholders. This shift requires companies to rethink their manufacturing processes and business models for optimal efficiency and sustainability. Role of switchgear in a growing power sector. With global electricity demand rising due to industrial and population growth, switchgear's role in the power sector, especially in transmission and distribution, is becoming increasingly crucial. The switchgear industry must adopt sustainable practices focusing on decarbonization, eco-design, high efficiency, and a sustainable supply chain. Although high initial costs and the complexity of installations pose challenges, there are significant opportunities for innovation and development for switchgear OEMs. Traditional air-insulated switchgear AIS, medium-voltage switchgear has traditionally been air-insulated, relying on air gaps between phase conductors to achieve dielectric stability. While AIS has been the standard solution, it is susceptible to environmental conditions, requires more maintenance over its lifetime, occupies more space, and takes longer to install. Transition to gas-insulated switchgear GIS. Over time, electrical distribution technology has shifted from AIS to gas-insulated switchgear. GIS is preferred in constrained spaces such as small rooms, offshore platforms, rooftops, and industrial settings. Its compact, secure design makes it ideal for urban expansion and areas where space is limited. Advantages of GIS. Faster installation. GIS systems are generally lighter and smaller than AIS, leading to quicker installation times. GIS requires minimal maintenance, reducing the risk of human error as newer personnel learn the equipment. GIS technology significantly lowers the risk of arc flash incidents. GIS enhances the reliability of medium-voltage switchgear, making it a preferred choice for new installations and upgrades. Key benefits over AIS. Compact footprint. GIS occupies much less space compared to AIS. Environmental reliability. GIS performs reliably in highly polluted, offshore, and saline environments. High reliability and fault resistance. With live parts unaffected by the environment, GIS is more reliable than AIS. Minimal maintenance. GIS has no exposed live parts or withdrawable components, making it a place-and-forget solution. Easy installation. The compact size and fewer moving parts of GIS make its installation faster and easier than AIS. Environmental impact by gas-insulated switchgear. Advantages of GIS in power transmission. GIS systems are now crucial in power transmission and distribution networks, with all components interconnected and insulated via compressed SF6 gas. Their compactness and metal shielding offer significant land use savings, aesthetic appeal, low radio and audible noise emissions, and enable urban substations close to loads. Properties of SF6 gas. Sulfur hexafluoride SF6 is a slow-reacting gas with high molecular weight, offering excellent arc extinction properties. It is chemically inert, non-toxic, and non-flammable in its normal state, making it an environmentally safe material that does not adversely react with biomass. GIS provides numerous advantages over AIS, including a compact footprint, environmental reliability, high fault resistance, minimal maintenance, and easy installation. Despite the environmental concerns associated with SF6 gas, its use in GIS enables space-saving and reliable power distribution, making it a valuable component of modern power transmission and distribution networks. When subjected to high-pressure conditions during electrical discharges, pure SF6 can dissociate and form toxic byproducts. Over recent decades, the extensive use of SF6 in the electrical grid has significantly contributed to its increasing atmospheric concentration. SF6 is a potent greenhouse gas with a high global warming potential, and its presence in the Earth's atmosphere is rapidly rising. Without proper disposal methods, all SF6 produced will eventually end up in the atmosphere, necessitating new policies for safe handling and component design, such as the use of hermetically sealed equipment and alternative gas mixtures, to ensure both personnel safety and long-term environmental protection. It is important to note that while these products are manufactured under controlled conditions in industrialized countries, they are sold worldwide, including in countries where F-gas regulations and similar legislation are not enforced. This makes end-of-life disposal particularly uncertain, especially when used equipment containing SF6 gas is exported to developing countries, where unqualified personnel may dismantle it. GIS role in shift to renewable energy. The expansion of renewable energy is driven by continuous governmental support and increased competitiveness of wind and solar PV technologies. Gas-insulated switchgear GIS plays a crucial role in this transition and is expected to see significant growth as new renewable projects are launched. Unlike thermal power stations, renewable energy installations require more switchgear within the electricity grid, as it takes numerous solar panels and wind turbines to produce the same electrical output. Consequently, as renewable power generation increases, the use of GIS will also rise exponentially. Alternative solutions for reducing SF6 usage. N2SF6 gas mixture. While mixing nitrogen N2 with SF6 can reduce the amount of SF6 used, this solution still relies heavily on SF6, making it less ideal for significantly reducing the environmental impact. CO2 plus O2 gas mixtures, typically composed of 90% CO2 and 10% O2, this mixture has a global warming potential GWP of 1, making it 23,500 times less impactful than SF6. However, its dielectric and arc quenching capabilities are significantly lower than those of SF6. Fluoronitriles gas mixtures. These mixtures, which include Novec 4710 fluid C4F7N combined with N2, O2, or CO2, vary by application and manufacturer. Although they offer better environmental performance, their dielectric strength and interruption capabilities are still inferior to SF6, requiring higher operating pressures. The minimum working temperature is -25 degrees Celsius. Fluoroketones gas mixtures, containing Novec 5110 fluid C5F10O with O2 and CO2, these mixtures also vary based on application and manufacturer. A significant limitation is their high dew point, restricting the minimum ambient working temperature to -5 degrees Celsius at nominal pressures. Their dielectric and arc quenching capabilities are inferior to SF6, necessitating higher pressures and limiting their use to indoor applications. Clean air with vacuum interrupter. Clean air, composed of approximately 80% N2 and 20% O2, has 0 GWP and is free from moisture and contaminants. However, it is significantly inferior to SF6 in dielectric strength, about 45% at the same pressure and arc interruption. Therefore, it requires higher pressure and the use of a vacuum interrupter 6 for effective interruption and insulation. Current challenges for SF6-free technology. There are various ways for SF6 gas users to reduce or eliminate SF6 emissions. Proper training, handling procedures, and emission-free equipment greatly mitigate SF6 emissions. However, due to its high global warming potential, the industry recognizes the need for alternative solutions. Advances in technology and extensive R&D have enabled original equipment manufacturers (OEMs) to develop switchgear operating with various SF6 alternatives. Transitioning away from SF6 switchgear is inevitable but slow due to several challenges. Higher costs. SF6-free alternatives can be more costly to produce than SF6-based circuit breakers. Utilities will need significant investments to replace existing SF6 switchgear. Limited availability. SF6-free switchgears are still relatively new, with limited market options. Transition strategy. Utilities face the challenge of safely and optimally transitioning to non-SF6 technology while maintaining equipment reliability, following decades of experience with SF6 circuit breakers, and staying flexible for future gas technologies. Technology selection: there is no consensus on which non-SF6 technology to pursue. Manufacturers choose different pathways without a unified approach, leaving end users without a clear direction. The best alternative is still undetermined. Addresses the above challenges. Field experience: utilities require extensive field experience, not just lab certifications, for new switchgear. This creates a cycle where manufacturers need field experience to sell new non-SF6 switchgear, but utilities need proven non-SF6 switchgear to install in their networks. Hybrid SF6 switchgear. Hybrid switchgear combines components of traditional air-insulated switchgear AIS and SF6 gas-insulated switchgear GIS. It features a compact, modular design that integrates several functions into one module. The introduction of vacuum technology questions the need for withdrawability, leading to a fixed breaker design with a disconnecting switch in series for isolation. Take example of TAMCO, who developed 36 kV hybrid GIS switchgear GV3N, which uses 30 to 50% less SF6 gas compared to conventional 36 kV GIS. This hybrid switchgear includes a vacuum interrupter in a gas-filled sealed tank, offering flexibility and customizability. It can be used for extensions or substitutions in traditional substations with air-insulated busbars. Hybrid GIS switchgear advantages: air-insulated busbar, inexpensive and reliable, assembled quickly without SF6 handling, making it environmentally friendly. All live contacts in SF6, ensures maintenance-free operation, reducing life cycle costs. Factory pre-assembled and tested, ensures high quality, minimizes on-site installation time, and reduces the need for skilled on-site resources. Substation modularization offers cost and time savings, reduces design errors, and provides predictable costs. Space saving and reduced civil works, saves up to 50% of space compared to conventional AIS substations, reducing foundation, steelwork, and cable trenching needs. This modular hybrid design offers a sustainable solution until the industry. Conventional versus hybrid GIS: 40 to 50% reduction in SF6 gas consumption. Features hybrid GIS technology. SF6 gas insulation with VCB, utilizes SF6 gas insulation combined with vacuum circuit breakers VCB for effective short-circuit current interruption. Compact design, occupies a smaller floor area and has a low carbon footprint. Minimal maintenance, features a sealed for life contact system, reducing maintenance needs. Safety, equipped with touch-proof screened busbars in air for enhanced safety. Adequate cable termination height, provides ample height for cable termination. Plug-in cable termination, includes plug-in type cable termination and test facilities. Modular design, offers modular design with the capability for extensions on both sides. Reliability, designed for high reliability with minimal maintenance requirements.